User notes for section 8.3. It's on a couple different things, both p-series and the integral test. We're actually going to start with the integral test. So take a look at the series that's given here. The sum as k goes from 2 to infinity of ln of k over k. So far, we've only talked about two different types of series. We know if it's geometric, we can tell if it's converging or diverging. We also know how to work with a telescoping series where most of the terms cancel out and we're left with a finite number of terms to show that it converges. But if it's anything else, if it's not one of those two, we don't yet know how to take care of it. So if we try to mess with this, if I just plug in values, I've got ln of 2 over 2 plus ln of 3 over 3 plus ln of 4 over 4 plus ln of 5 over 5 and so on. So notice none of them are negative, so I can't cross anything out. So it's not telescoping. And if you try to think of what do I multiply this by to get here, and then do I multiply the same thing to get over here, you're not going to come up with anything. It is not geometric. It's not telescoping. We could check the limit as k goes to infinity. That's one other thing we've talked about. So that'd be ln of k over k. I have to use Hopital's rule, so it's 1 over k over 1. Which is 1 over k. If I plug in infinity, I get 1 over an infinitely big number, which goes to 0. Remember, if this is anything but 0, we can stop right there and say that this diverges. But just because it is 0 does not mean that it converges. So we did the nth term test for divergence. We checked geometric. We checked telescoping. It's not any of those. We can't take care of it with any of those. We're going to need some more methods to take care of a series that looks something like this. And we are going to take a look at the integral test. The integral test says that if k is positive, or if f, if the function is positive, continuous, and decreasing for all values greater than or equal to 1, and the sequence is equal to the function. Basically, this right here and this right here are the same thing. The sum as n goes from 1 to infinity of a sub n, and the integral from 1 to infinity of f of x dx either both converge or they both diverge. One of those two things need to happen. So usually we'll be looking for this. We want to know, does this converge or diverge? And what we can do is we can check the integral. And if the integral gives us a number, that means that the sum converges. If we can show that the integral does not exist, it diverges, then this diverges as well. Most of this stuff isn't terribly important. It does always need to be positive, or at least eventually become always positive, because if I can show like x is greater than 4 and this is a 4 and this is a 4, then they would always converge. Also, if f is always negative, you could just take a negative out, and then show that they both do it as well. It does need to be continuous on the interval, which almost always it will be. I guess it will eventually take a look at one where it's not. And it does need to eventually be decreasing. It needs to be getting smaller and smaller and smaller. Although if this is always negative, you want it to be getting closer and closer and closer to 0. Really, the big thing is we're going to check this integral. If it converges, this guy also converges. If it diverges, this also diverges. Bottom number, it doesn't have to be 1, 1, 1. This could be 4, 4, 4, 72, 72, 72. Or, for this one here, 2, 2, 2. So this one gives us the sum as k goes from 2 to infinity of ln of k over k. Notice we are not continuous at k equals 0. K equals 0 is not on my interval. We could prove, so it is continuous. We've kind of shown that they're all positive. If I plug in anything bigger than 2, I'm going to get positive on the top and positive on the bottom. We could take the derivative of this and prove that it is always decreasing. Take my word for it. You don't need to worry about that right now. But let's take a look at how the integral test works. So we have the sum as k goes from 2 to infinity of this function. What we're going to do is we are going to integrate from 2 to infinity of that same function. Evaluate that integral. We've evaluated integrals with infinity in one of the bounds. We did that in a previous section. In this case, you want to make u equal to ln of k. So your du is 1 over k dk. So here I get u du. You can either change your bounds or change back. Let's go ahead and change our bounds. So if I plug in 2 for k, I get ln of 2 for my bottom bound. If I plug in infinity, the natural log of an infinitely big number is still infinitely big. Integrate gives me 1/2 u squared. Evaluated from ln of 2 to infinity. Plug in infinity, I get infinity squared times 1/2. That's infinitely big minus some number. So this does not exist. This diverges. There is an infinite amount of area under there. Therefore, this diverges as well. This one asks us to apply the integral test to the series. Let's change this one a little bit. I'll write that as squared here. So the sum as n goes from 2 to infinity of 3n over the quantity n squared minus 2 squared. If I didn't change that to minus 2, we would have been undefined at a point in between on my interval. This one's undefined at root 2, which would have been on the interval, but it's not on the interval from 2 to infinity. So to do this, we're going to evaluate the integral from 2 to infinity of 3n over n squared minus 2 squared. To do that, we want to u substitute, making u equal to n squared minus 2. My du is 2n dn. Got 3n dn. Didn't write my dn, but so I need to multiply by 2. I'm also going to multiply by 1/2. 2n dn. That's my du. This 2 is my bottom bound there. I got confused for a minute. I've got this 3 on the top. I'm going to move that 3 out front. This is 1 du over u squared. Change your bounds. If I plug in 2, I get 4 minus 2. If I plug in infinity, I get infinity squared minus 2. That's an infinitely big number. Integrate. 3/2 the integral of u to the negative second. Add 1 to the exponent. Divide by -1. So I've got -3 over 2u. Plug in the top bound. If I plug in infinity, 3 over infinity goes to 0. Plug in 2. -3 over 4. So this integral gives me 3/4. This integral converges. If the integral converges, the sum also converges. They don't necessarily converge to the same thing. Just because the integral is 3/4 does not mean the sum is 3/4. But we do know that it converges to something. You will not be asked to find what it converges to unless it is telescoping or geometric. Right now, we just want to know, does it converge or diverge? Example 2 here asks us to apply the integral test to determine the convergence or divergence of the series. It does not give us the rule for the series, so we're going to have to come up with the rule. Looks like the top is always 3. The bottom is, I start at 5, and then plus 3, plus 3, plus 3. So I'm adding 3 over and over again. And if I plug in 1, I want to get 5. So 2 plus 3n is the rule there. I'm starting at 1, and I'm going up to infinity. And again, you can kind of check this. If I plug in 1, I get 3 over 5. Plug in 2 gives me 6 plus 2, 8 on the bottom. Plug in 3, 9 plus 2, 11 on the bottom, and so on. It tells us to use the integral test. So let's do that. Notice these numbers are always positive. They're always getting smaller. 3's on the top, and then bottom numbers are getting bigger. So this is decreasing. It is continuous everywhere except at negative 2/3, which is not from 1 to infinity. So it is continuous, positive, and decreasing. So we are going to integrate from 1 to infinity of 3 over 2 plus 3n dn. Use substituting. Gives me, that guy there is my du. 1 over u du. If I plug in 1, I get 5. Plug in infinity times 3 plus 2. Integral of 1 over u is ln. Plug in infinity. Natural log of an infinitely big number is also infinity minus ln of 5. This diverges. The integral diverges, therefore the sum diverges. All right, what I want you to do right now, and this should not take as long as it might initially look, is to pause the video and to relatively quickly decide if each of these converge or diverge using the integral test. Once you think you have them, go ahead, start the video back up. I'll show you a couple of them, and we'll talk. All right, so for one like this, we're integrating from 1 to infinity of n squared dn. If I move the n to the negative second up to the top, so I add 1 to the exponent. Plug in infinity, so I get infinity minus something. This one diverges. You should find that this one diverges, this one diverges. This one would be u to the negative 1/2. Add 1 to the exponent, divide by 1/2. Square root of infinity is still infinitely big. This one diverges, this one diverges. Integral of 1 over n is natural log. Natural log of infinity, this one diverges. If I make this n squared though, now this is negative 1 over n. If I plug in infinity, now I get 0 minus negative 1. This one converges, this one converges. So the question is, where does this rule where all these diverge and then it flips over and now they're all going to converge? Because here I've got like n to the negative 3rd dn. So add 1 is n to the negative 2nd, so I get negative 1/2. And notice I've got n on the bottom again, so when I plug in infinity, it goes to 0. So all of these, if I have 1 over n to an exponent, it doesn't have to be a 1 here. If this was a 2 or a 78, it's going to give you the same thing. It's really the important part's the bottom, n to an exponent. This is called a p-series. The sum, as n starts at 1 and goes to infinity, of 1 over n to the p. will converge. Notice any value bigger than 1 is going to make it converge. N to the first. If I have n to the 1.01, if p is 1.01, it would look like this. 1 over n to the 1.01. So it would be the integral of n to the negative 1.01. Add 1 to the exponent. Notice my n would get moved down to the bottom again, right? So when I plug in infinity, because I'm dividing by an infinitely big number, that part's going to go to 0. So it's converging for any p values greater than 1. Notice n to the p is on the bottom here. If p is greater than 1, it converges. If p is any number less than or equal to 1, including any negative number, including 0, including 1 itself, then it will diverge. I want you to grab your book if you have it. If not, I'm going to write the problems down. We're going to talk through some of these in your textbook on page 582. Page 582, starting with number 56. So we have all these different methods that we can use to check if these are going to converge or diverge. So 56 says 3 times the integral as n starts from 1 and goes to infinity of 1 over n to the 0.95. 1 over n to the 0.95. Hopefully we recognize that this is the case that we were just talking about. This is a p-series. 1 over n to the p. If p is less than 1, if p is anything less than 1, this diverges. So I would state that this diverges. You are going to have to give a reason. I would state that it is a p-series with p less than 1. 58. 58 says the sum, as n goes from 1 to infinity, of 1.075 to the n. 1.075 to the n. Couple different ways you could do this. The first, if I have a number to the exponent, that means I'm going to take the previous term, and I'm always multiplying times 1.075 over and over again. So this is a geometric series. It is geometric, and our R value, the value that we're raising to an exponent, the value we're multiplying by over and over and over again, is greater than 1. Therefore, it diverges. Diverges, it is a geometric series where the common ratio is greater than 1. Another way you could do this is show that the limit as n goes to infinity of 1.075 to the n, 1.075 to an infinitely big number diverges, therefore, or does not exist, therefore the series diverges. So that's the nth term test for divergence. Number 60. Number 60 is the sum as n goes from 1 to infinity of 1 over n squared minus 1 over n cubed. You can split it into two separate integrals or two separate series. This is the same as the series as n goes from 1 to infinity of 1 over n squared minus the sum as n goes from 1 to infinity of 1 over n cubed. 1 over n squared is a p-series. P is greater than 1. Therefore, this part converges. This part also converges. Therefore, subtracting those two will converge. Each part is a p-series. With p greater than 1. 62 says the sum as n goes from 1 to infinity of ln of n. easiest way to do this would be to show the limit as n goes to infinity of ln of n does not exist. It's just not equal to 0. The only time that it can converge is if the limit as n goes to infinity of the sequence is 0. It has to be 0 to converge. Just because it's 0 doesn't mean it does converge, but if it's anything but 0, then the series diverges. And again, that is called the nth term test for divergence. '64 asks for the sum as n starts at 2 and goes to infinity of ln of n over n cubed. I don't have anything to the n power. It's not geometric. If I start plugging numbers in, ln of 2 over 8, ln of 3 over 27. It's not telescoping because these are always positive. We said it's not geometric. We could evaluate the limit as n goes to infinity. 1 over n over 3n squared, which is 1 over 3n cubed. As n goes to infinity, this does go to 0, which I can't stop and say diverges, but I can't guarantee that it converges either. So the nth term test for divergence is out. It's not a p-series. So the only other thing we can maybe do is integrate it from 2 to infinity, ln n over n cubed dn. This is not just a straightforward u substitution. I can't make u equal to ln of n because then I'm going to have 1 over n. So we are going to do it by parts. Logarithms before algebraic functions. So my natural log of u is, or natural log of n is u. N to the negative third dn is dv. Derivative of natural log is 1 over n. Integral of n to the negative third is negative 1/2 n to the negative second. The rule is u times v. So if I multiply these two, this is the same thing as negative 1 over 2n squared. So I get negative 1 over 2n cubed minus the integral of v. I'm sorry, u times v. I messed that up. U times v minus the integral of v du, which is the part I just did, 1 over 2n cubed. Negative, negative, I changed that to plus, 1 over 2n cubed dn. We can go ahead and integrate this part over here. So we've got n to the negative third. Add 1 to the exponent. Divide by that. Dividing by negative 2 changes it to minus, and 4 on the bottom here. N to the negative second, I'm going to move it down to the bottom here. Now we plug in infinity. Notice when we do plug in infinity, I erased it, but to plug in infinity here, we would use Hopital's rule, which we showed earlier was 0. Limit as n goes to infinity. If I plug in infinity, I get infinity over infinity, so I take the derivatives, 1 over n over 4n. negative 1 over 4n squared. So this is 0. So if I plug in infinity here, it will go to 0. If I plug in infinity here, 1 over an infinitely big number, that's 0. If I plug in 2, I get something. I don't even care what that is, but I do get something, right? I get a number here. Therefore, it converges. Because the integral exists and the integral converges, therefore the sum converges. That's it for today's notes.